So what will be the strategy? What will be the strategy to choose a particular column for separation of volatile sample? So there are actually 6 points which we have to keep in mind. Now we are doing, why we are actually, why we are strategizing our column. We want to have the best resolution. We want to have best resolution. We want to have very good Gaussian peaks. Okay, and at the same time we should have shorter analysis time. Shorter analysis time. So we are doing all these optimization. We have also done certain optimizations when we were talking about the illusion chromatography. Similarly, because this column is actually the heart of separation, so we have to select our column. Okay, that is why we actually are dwelling into this. So first of all, the most important thing, the nature of analyte. Now again, the same concept, that is the like dissolves like concept. So if we have a polar analyte, then we have to choose a polar phase. Okay, for example, if our analyte has OH groups, has COH groups, have ethereal linkages, then we choose polar phase. For example, like the previous one, that is the polydiethylene glycol, or the succinate, polyethylene disuccinate, that is called as DEGS. Similarly, if we have a non-polar analyte, for example, simple hydrocarbons are there, then we have to choose the non-polar phase, like the one previously one, that is called as polydimethyl siloxane. So that is very important, because this analyte prefers that type of phase in which it forms good interactive bonding. Again, the boiling point range. We have already discussed that if the different analytes have close boiling points, then we have to use an isothermal conditions. That is, we do not have to increase the temperature of our column. But at the same time, if the temperature range is different, you can say that if the two components have a good difference in their boiling point, then we can do temperature programming. And by temperature programming, what we do, we actually get shorter runs. Okay, so this is the aspect that we have to look into the boiling point of analytes also. Similarly, with regard to sample efficiency. Now, if for example, if we want to achieve very high efficiency, then we have to use capillary column. Okay, we have to use capillary column to achieve high efficiency. But at the same time, if we are using capillary column, then we cannot take too much sample. If our sample size is high or it is large, then we have to go for the packed column. But the moment we go for packed column, the efficiency will be compromised. So each time we have to do some meticulous selection. Okay. Similarly, with regard to column length, we know that greater the number of the theoretical plates as per the plate theory given by Martin and Sinch, the Nobel laureates in this field, the Nobel Prize winners in separation science. They propose that, and we know that we have actually from the Van Demeter equation we have experimentally verified that the greater the number of theoretical plates, higher will be the resolution, and the number of theoretical plates can only be maximized when we take longer columns. So high resolution will be there, but at the same time resolution will be high. Good, you will get well separated peaks. But at the same time, you can see that the TER increases. That is, now you have to do longer analysis. You require longer times for your analysis. Okay, but at the same time, if you take smaller columns, shorter columns, then of course you will get faster runs. But at the same time, the resolution will be compromised. So every time you have to look your utility, which type of sample is running and in which conditions, and what are your requirements, what are your objectives for a particular set of separation. Similarly, film thickness also comes into play, that if the stationary phase thickness is too high, that is if it is greater than 5 micrometer, then it is going to have good interaction or strong interaction of your solutes with the stationary phase. That is, your volatile components are going to stay longer. That is, they are having high TR. High TR. Okay. If they are taking high TR, then it means that there are also chances of they may get adsorbed. There are chances because your film is actually thick now. Similarly, if because of high TR, your analysis time is high, or you can say elution will be slower. Okay, but at the same time, if you take thin film, then of course you will get faster elution. But because of the faster elution, resolution may be compromised. Or you can say that there are chances that RS may be less than 1.5. Okay, so you have to keep everything in mind. Again, the concepts of the elution chromatography holds good in case of gas chromatography. That is what you have to look for. You have to look for the rate, you have to control the broadening of the peak, and at the same time you have to have as much distance between the peaks as possible. So that is your best resolution. So what you have to think? You have to think of retention factor again. You have to think of selectivity factor again. And you have to think for resolution, that is RS again. Because all those concepts hold good here also. Similarly, an example is that, for example, if we have to separate a mixture of alcohols, we know that alcohols are polar compounds. Then you have to choose some polar stationary phase. And Carbovex, that is the trade name of polyethylene glycol. This is the trade name of polyethylene glycol. Polyethylene glycol. You have to take, okay, you have to choose you can say polar phase. Similarly, if you have a mixture of hydrocarbons that are non-polar, then you have to look for some non-polar stationary phase. And we have already discussed this, that is the polydimethyl siloxane is an example. So what you have to do, you have to have a balance. You have to have an equilibrium between efficiency, selectivity and analysis time. Okay, the same thing which we have discussed while talking about the column optimization in elution chromatography. So almost the same concepts apply here. So what actually determines the heart of separation? That is, what actually determines the column? That is how actually we can separate two volatile components of a mixture. So again, the important aspect is the stationary phase. It is the stationary phase on which different components interact, and on the basis of interaction they have different elution rates, and because of the difference of different elution rates, they go out from the column at different times, and the difference in elution give rise to difference in peaks. So the basic or the most vital part of any gas chromatograph is the column, and the efficiency of any or the success of separation of any gas chromatograph depend upon the efficiency of its column. So what we have to remember, what we have to actually look, we have to look for selectivity. That is, we have to look for the value of alpha. That must be greater than alpha, must be greater than, it must be greater than unity. Alpha must be greater than unity. Similarly, we have to think of retention time. Because if now retention time is again tricky. If the retention time is too much between the components, then you have to do certain programming. Okay, but if retention time is not too much, then you have to run your column in an isothermal condition. Okay, similarly, peak resolution, that peaks must be well resolved. That is, always RS must be greater than 1.5. Okay, similarly, you have to keep an eye on the thermal stability. That is, your stationary phase must be thermally more stable as compared to your volatile components. Or you can say your stationary phase must be very less volatile as compared to your sample. And a clear marker is that your stationary phase have at least 100-degree greater boiling point than the components of the volatile mixture. That is the golden rule. Okay, golden rule for column temperature was 50 degrees centigrade, and for a stationary phase it is 100 degrees centigrade. So you have to remember this golden principle with regard to the thermal stability of the stationary phase. Similarly, let us have a broad classification of stationary phase in GLC, that is the gas chromatography, or simply the gas chromatography. So we have summarized this table in terms of polarity, we have summarized in terms of chemical composition, and in terms of functional group. So in terms of polarity, let us discuss in terms of polarity. For example, if we have a non-polar stationary phase, and the example is Se30 or OV70, or maybe let us suppose Se30, that is called as the polydimethylsiloxane, then it is good for the separation of hydrocarbons. Similarly, if we have a moderately polar stationary phase, moderately polar, for example OV17, or the one which we have seen, which we have drawn the structure of that is called as the polyphenyl methyl siloxane. Because phenyl, because of the presence of pi electron, it actually favors the pi interaction with the solute, so it becomes moderately polar. So an example is OV17, and it is good for the separation of various ethers which are not non-polar exactly or not so polar. So an example is the moderately polar, the ether. You can separate different ethers, not exactly the balanced ethers. That is, you cannot separate diethyl diether, or simply where both the functional groups are the same. So you can separate, of course, ethers also. Similarly, if you have a polar stationary phase like the carbovax, that is the polydimethyl glycol, then you can separate all the polar compounds like alcohol, like esters, you can separate them simply. Similarly, if by chemical type, for example silicon, polyethylene glycol, again polar, polyester, again polar. So these examples are OV1, these are the trade names. You have PEG, that is polyethylene glycol. You have the DEGS, that is the succinate derivative of the diethyl glycol, and this is actually good for all the general separation. Now in terms of functional group, for example, this is hydrocarbon, this is again non-polar. Cyano group, highly polar. Ester group, phenyl group, polar. So the examples are OV101. These are the trade names actually. Now, example are they have a specific selectivity. So what you have to do, you have to remember that you have to choose in terms of analyte polarity, that your given analyte which is present in the sample is polar, non-polar or partially polar, that is moderately polar. So you have to decide your stationary phase in terms of the polarity. Similarly, you have to decide in terms of volatility, that is how much stable it is. We will see in the coming slide about the stability, and also the interaction strength. And the interaction strength actually why that depends upon that light dissolves like concept. If you have polar, it will prefer polar. If you have non-polar light, it will prefer the non-polar stationary phase. So these are the actually stepping stones for making or for taking into account before running the actual column. Now let us go into the detail with regard to polarity. So the underlying concept is light dissolves light. This is the main principle which we have to account every time. Now for example, if you have a 100% methyl silicon, then the trade name is Se30 or OV1. Then here actually it is a non-polar you can say stationary phase. Now if you have a non-polar components, then of course their interaction is good. For example, hydrocarbons or esters or ethers, like the diethyl ether, or like this. Suppose you have to separate it, then this is actually non-polar. Now for example, if you have to separate this, then you can separate on the basis of the difference in the boiling point here. There must be difference in the boiling point. So the selectivity here is the boiling point, because you have chosen the stationary phase and you have chosen the analyte which is also non-polar. Similarly, if you have a moderately polar phase, for example methyl phenyl silicon, that is called as OV17, the one which we have already discussed, like this. This is like this. This is like this. Since it is poly, and let us draw the conjugation here. Because of the presence of this group, this phenyl group, because of the presence of this phenyl group, it gets an ability for pi interaction, and that is why it becomes moderately polar. And the trade names are OV17 and OV225. So here the selectivity is that here the dispersion also comes into play and the dipole interactions also comes in. That is the pi-pi interaction. So this is good for the separation of aromatic compounds or the halogenated compounds. Okay. So let us see a polar phase now. Polyethylene glycol. Polyethylene glycol means it is like this. Now you can see there are a lot of hydroxy group imparting it highly polar nature. So nitrile silicons, now that is the CN, and the trade names are the Carbovax 20M or QF1 for nitrile. So it is good for the separation of alcohols, acids, amines. Now here it is the hydrogen bonding. The interaction or the selectivity is because of the hydrogen bonding. For example, if you have an amine comes into play, let us draw a more clear picture here. For example, this is for example, here it is N. Now, for example, if an amine comes into play, let us suppose now, for example, this is the amine, this is amine part, and this is your polyethylene glycol. Now, there are chances of hydrogen bonding here, chances of hydrogen bonding here, and this is actually gives you selectivity, or there may be chances of dipole-dipole interaction. So, the important thing is that polarity of a stationary phase must match with the polarity of analyte for effective separation. That is again the principles of like dissolves like. That is, polar will prefer polar, non-polar analyte will prefer non-polar stationary phase, and the moderate will prefer the moderate one. Simple. So, simply now classification based on chemical composition. We have already discussed OV1. These are the examples of silicon where the polarity, or you can say the non-polar one. Similarly, they are thermally very stable, and because of the high thermal stability, the bleeding, or you can say the chances of decomposition of stationary phase are minimal. That is low bleed. That is, your stationary phase will remain stable up to 350 or 400 degrees centigrade. We are going to see the effect, the temperature, the stability with regard to temperature in the coming slides also. And the application is, that is, you can separate journal organic compounds. Similarly, if your polyethylene glycol, they forms non-polar phases, and the trade name is Carbovax or PEG 6000 polyethylene glycol. This is very good for the separation of oxygenated compound, because here the pi-pi interaction and the dipole-dipole interaction comes into play. Sometimes hydrogen bonding, weak hydrogen bonding also comes into play. So, again non-polar, example of polar. So, polyester based, that is called as diethylene glycol succinate. It is also a derivative of polyethylene glycol. Similarly, you can separate fatty acids, esters, you can separate fatty acids. Similarly, you have certain custom based beads, that is specific. For example, the cyanopropyl or the trifluoropropyl silicons. Now, because of the induction of a specific group, you have actually facilitated a specific type of interaction. And now you can even separate complex mixtures by inducing specific groups. So, these are the custom based, okay, depending upon the nature of the chemical structure of the analyte. So, what are important factors? That is polarity. You have to look the polarity. Similarly, you have to look for the temperature limit. That is the temperature limit of the stationary phase, and it must be 100 degree greater. Otherwise, column bleed maker. Similarly, film stability. That is, it should be stable. It should not, go along with the analyte. So, classification based on the functional group. So, for hydrocarbons, if you have the functional group of hydrocarbons, maybe alkane, alkenes or alkynes, now you have to choose always OV1, that is the dimethyl siloxane, and the dominant interaction are simply the dispersion forces, and it is good for non-polar analytes. Similarly, the moment you introduce phenyl group, we have seen it, the moment you introduce phenyl group, you actually introduce the pi-pi interaction, and an example is the OV17, and it is good for the separation of the aromatic compounds. Similarly, if you've introduced a electronegative group like the cyano group, the CN, now you actually facilitated the formation of dipole-dipole interaction. That is, and it is good for the separation of nitriles and alcohols, OH. Similarly, ethers and esters. Here, hydrogen bonding actually becomes dominant, and again, it is good for separation of esters and the carboxylic acids. Similarly, if you have ether linkage and the two arms are not balanced, then you can separate it on some polar resin or polar stationary phase, and again hydrogen bonding is effective here. So alcohols, amines, etc., because it facilitates the formation of hydrogen bond. So hydrogen bond forms when hydrogen comes in between two electronegative centers, two electronegative atoms, you may also call it. So the important thing is that if you have a good interaction, then you will get sharp peaks if your interaction is good. Okay, for example, if you have a combination of a polar or non-polar polar, then you will get sharp peaks, you will get Gaussian shaped peaks. That means your resolution will be very good, you have a very good resolution. Okay, so the matching analyte chemistry implies a sharper peaks or high resolution. Sharper peak means good resolution. That means you have effective separation of analytes, and in case of GC, effective separation of various volatile components. So what you have to bear in mind? You have to bear in mind the golden rule of chemistry, that is, like substance dissolves its like substance. Okay, so classification on the basis of phase. Now for example, there are three actually key features with regard to the physical form. For example, if you have a coated one, then the liquid film coated on the support, it must be inert, and we have seen that in case of wall coated open tubular columns. The wall coated open tubular columns, the advantages are its simplicity, and they are very economical, they are very sturdy also. Similarly, the bonded one, where the chemically bonded to surface, and if they are chemically bonded to surface, then of course there are absolutely zero chances of bleeding, and they are solvent resistant. Okay. Similarly, if they are cross-linked, that cross-link actually provides specificity. For example, if you have a cross-linked porous structure, then they are very effective, and give you very stable type of interactions, and the columns will have long life also, extended life. So what is the important point is that if you want to enhance the film robustness, then you have actually reduced the bleed during the temperature programming, or during the increase in temperature, But the important point which you have to remember at this stage is that your stationary phase must be highly stable. That is, in terms of boiling point, it has 100 degree above than the boiling point of any component of the separating mixture. So let us see in terms of the selection that how we are going to maximize the resolution and how we are going to procure the ideal peak shape, that is the sharp peaks having Gaussian shape. So if your analyte are hydrocarbons, then you have to choose a non-polar phase so that the interaction will be good. An example is OV1, polydimethyl siloxane. Now if your analyte, or if your volatile mixture consists of aromatic hydrocarbons, then you have to choose some moderately polar phase. For example, polyphenyl methyl siloxane, the one which you have procured by replacing one methyl group by one phenyl group. So here you have chosen a moderately polar phase, and the polarity match is partial, and an example is OV17, that is the trade name. Similarly, if you want to separate alcohols, then we know that now you have to choose some polar phase. For example, polydiethylene glycol. Now here again the interaction will be very good because you have polar-polar combination. Example is carbovex. Similarly, if you have esters or acids, then you can take polar and polarity image will be high. For example, succinates. For halogenated one, you have to choose some moderate phase, like the one you have chosen for aromatics. An example is OV225. So you have to keep in mind the nature of your analyte, and on the basis of your nature of analyte, you have to choose the phase so that you can have a good matching of it. Okay. What are the summary points from all this discussion? That the most important and the most vital point of effective separation through any gas chromatographic column is the polarity. That polarity is the prime factor, the most important one. Similarly, the chemical composition, because it determines the stability, thermal stability also. Now, if you have functional group, then you can fine tune them. You can select them. Which we have seen that if, for example, by induction of a CN group, you have make a selectivity. Similarly, phase form, it imparts durability. It imparts long lastiveness. So the right match, what you have to ensure? You have to ensure high resolution and reproducibility. That is, for 2 experiment, your peaks, the number of peaks and the area under the peaks remains the same. It must be same for 10 runs, it must be same for the 20 runs, 50 runs. That is, you have a very good reproducibility. Okay. So the point which is to be taken is that the stationary phase is very important, because it is the stationary phase which leads to the different interactions, and that different interactions give rise to different migration rates, and different migration rates give rise to different elution of different components, giving rise to different peaks in the chromatogram. So the most important is you have to choose a stationary phase very cleverly and very tactfully, so that you can achieve a best resolution. So with this, thank you very much, and we will be meeting again, and then we will are going to discuss the different detectors. Thank you.